All right, so in this video, I would like to prove three properties about limits of sequences. And I'm not so focused on what the theorem or propositions are saying. So you should learn them, but what I really want you to focus on in this video is how the definition of the limit is used to prove each of these statements. Um, that's what I want you to focus on, understanding the proof and how it's structured. I said the definition of the limit takes a little bit of practice and getting used to, and this is what the video is supposed to do. So this video might take a couple of watches to really make sense. But I want you to understand all of the proofs that's provided here. Let's jump right into the propositions. Okay, so the first thing I want to prove is this proposition. So if you have this, right? So you have two different sequences, AN and BN. And the BN, the distance from BN to L is within AN for all N. So the statement is true for all N. And you also know that limit of AN is going towards 0. So this number right here is getting closer and closer to 0. That must mean that the BN is approaching L, right? So this is a statement involving two different sequences, AN and BN. You already know what the N is approaching. N is approaching 0. That's given to us. And then we're supposed to show that the limit of Bn is equal to L, right? So we're going to use the definition of the limit twice, once for An approaching 0 and once for Bn approaching L. So I even wrote it out here. So focus on the definition of the convergence, okay? All right, so whenever we want to show something converges, we start with let epsilon greater than 0, because this is a universal quantifier for epsilon, right? So take epsilon as given, and then you'll come up with an n such that it gets to within epsilon. That's how we're going to do it. Okay, so let's set epsilon. It's given to us. And let's use the definition for the convergence of AN, the first sequence. Since the sequence A converges to 0, if you use the definition of the limit, there exists an N such that N greater than N implies the absolute value of AN is less than epsilon. So notice I wrote absolute value of AN here. So the limit is 0, so this is AN minus 0, but AN minus 0 is the same thing as AN. So I just wrote absolute value of AN here. So if this is true, AN is converging to 0, and we're given that that's true. So we have that. So we used the definition for convergence of AN. Now, let's see what that means in terms of the sequence Bn, okay? So if this little n is greater than the same n that's given to us here, then that means that, let's see, okay, so this part, this first inequality is given to us in the statement of the problem, okay? So that's a hypothesis. We already know that that's true. But AN, like, look, AN has to be positive already because it's a number greater than absolute value, right? Greater than or equal to. So that's equal to itself in absolute value. But we also know that if little n is greater than or equal to big N, that thing is less than epsilon. So now this has to be also true. But if you look at the chain of inequality, this expression over on the left is less than epsilon. So that's exactly what you have to show for the sequence Bn to converges to L. So by the definition of the limit, that shows that the sequence B converges to L. I hope that made sense. Okay. So if you have questions about any of these steps, please use Canvas or Discord and email me about some specific part about the argument, and then maybe I can go into more detail. I think Discord works best for this purpose because we can interact in real time. Okay, let's look at the second proposition. So in this proposition, we have two sequences, AN and BN, that they're both converging to different numbers, L and M. So if you have two converging sequences, then their sum, so now we have a third sequence, which is the sum of the first two sequences. And that has to approach the sum of the limits of the two sequences that are being added. So this seems pretty intuitive. If you have two numbers getting close to L and M, then the sum of the two things should be getting close to L plus M. Let's see if we can prove this. In this problem, we're going to end up using the definition for the limit 3 times. Once each for each of the sequence, and one more time for the third sequence, which is the sum of the two sequences. So let's see how that gets put together. All right, so we want to show it's a limit thing. We want to show that limit exists, so we start with let epsilon greater than 0. So let's use the definition for n converging to L. So we know that n is getting closer to L, which means there exists some natural number n1. So I'm making a name here because the n that's given in the definition of the limit might be different for different sequences. So we have n1 such that if you have an n greater than or equal to n1, then the distance to the limit is within, we usually write epsilon here, but if the limit exists, then you could choose epsilon to be whatever you want. So in this example, I'm going to use epsilon over 2, as you will see in a minute why. Okay, I mean, if it's true for any epsilon, then you could pick, instead of 1/100th, you could just choose 1/100th divided by 2, right? Okay, so we're going to do the same thing with the second sequence. Bn is approaching the limit m. So there has to be some point, I'm going to call this n2, so it doesn't have to be agree with n1, such that as long as you pass that number, you're within epsilon over 2 of m. So for the sequence n plus bn, what we're going to do is we're going to choose our n to be the maximum of n1 and m2. So that means if n is greater than this n is the bigger of the n1 and n2. So both of these condition is satisfied. This little n is greater than n1, and it's also greater than n2, because it's greater than whichever the larger one is. Okay, so now I want to show that the limit of the sequence n plus bn is equal to L plus m. So this is what we have to show, that this is less than epsilon. Okay, so the first step I'm going to do is to reshuffle the terms so that we have n minus L here and bn minus m. you just reshuffle it so that this is the first sequence part and this is the second sequence part. And then we're going to use the triangle inequality. This thing is less than or equal to this part plus this part separately. Okay. And we know that because the little n is greater than n1, this part is less than epsilon 2 over 2. This is given by that statement. And similarly, it's greater than n2, so this also have to be true. So each of those pieces is less than epsilon over 2. And if you add 2 epsilon over 2, you get epsilon total. So this thing is less than epsilon. So that shows this statement, right? The sum of the sequences is equal to the sum of the limits. Okay, and when you see the end, you might see why I chose epsilon over 2 to here and here. So it adds up to the epsilon. And this type of breaking up the limit into two pieces, where each of the pieces is controlled by epsilon over 2, is called epsilon over 2 type of argument. Right? So this is a technique. If you want to show that some limit exists, you could break it up into 2 pieces, or sometimes even 3 pieces, or even more. And each of those, if you can show that each of those are small enough, it adds up to epsilon overall. Okay, let's move on to the next theorem. All right, so this one is an important one. So it has a name. It's called Monotone Convergence theorem. Okay, so if you have a sequence that has 2 properties, so it's a bounded sequence, and it's also monotone. So if every bounded monotone sequence of real numbers has a limit. So those 2 conditions will guarantee that you have a limit. Let's remember, bounded means, in particular, it has an upper bound, right? Also, monotone means it's either non-decreasing sequence, so the numbers are either equal to or greater than 1 step before. So that's monotone. You could have a monotone that's non-increasing, where it's equal to or less than the step before. So if it's bounded and monotone, you should have a limit. That's what we want to prove. Okay, so it turns out that, so let's jump to the proof. The non-decreasing sequence here, argument for that is very similar to non-increasing sequence. So we're going to use the key phrase, assume without loss of generality, that we're considering non-decreasing case. So we're just going to prove it for this case, but the other case is very similar. You just have to flip inequalities to prove the same thing. Okay, so the sequence A is bounded. That's given to us in the hypothesis. So anything that has an upper bound has a least upper bound by the least upper bound property, or the completeness axiom. So you can find a supremum. Okay? We're going to call that supremum the limit L. So we're going to have to show that this is indeed the limit. Okay, so we have, so in pictures, this is what I'm imagining. Here's a non-decreasing sequence. It's getting larger and larger. And it's bounded, so it never passes that dashed point, right? So what it's going to get closer and closer to is going to be the least upper bound, the smallest number you can think of that it does not pass. So that's going to be our limit, L. Okay, so let's prove it. So every time I want to show that something is a limit, we start with let epsilon greater than 0. Since L is the least upper bound, we know that L minus epsilon is not an upper bound, right? Because it can't be, any number that's smaller is not an upper bound anymore. Okay, so if it's not an upper bound, that means there exists an n such that some number in the sequence is larger than the number that's not an upper bound. So A capital N is greater than L minus epsilon. Okay, so now I claim that this n will show that we're within epsilon of the limit. Okay. All right, so n greater than or equal to n implies, so we know that L minus epsilon is smaller than an, so that's exactly the same thing as this inequality, I just wrote it backwards. And because the sequence is non-decreasing, A sub n is larger or equal to than A sub capital N. And we know that A sub n is less than epsilon, less than or equal to less than or equals to L, because L is a least upper bound. In particular, it's an upper bound, right? It's a least greater than or equal to every element in that sequence. Okay. And of course, L is less than L plus epsilon because that's epsilon more than that. Okay, but what did I write? I've written that A sub n is squished between L minus epsilon and L plus epsilon. That's another way to write exactly this inequality. The distance from an to L is within epsilon. So we found an n where if you pass that n, you're within epsilon or the limit. So we are done. We found the limit. Okay, so those are 3 very challenging proof to digest. I hope you watch this video as many times as it takes to kind of understand what it's saying. It's also in the textbook as well. All right, this is where we're gonna end here. On Thursday, we're gonna have a fun topic that's a little bit outside of chapter 13 stuff. So this concludes the portion of the mathematics you have to know for the final exam. All right, see you guys later.